Hello and welcome back to differential equations, substitution methods, exact equations, and reduction methods or whatever. We are going to talk about exact equations right now. And we start with the criterion for exactness. And if that is fulfilled, we can perform this procedure. You learned this procedure earlier in Calculus 3, if you took Calc 3 before. And it's in Chapter 14 under the heading of finding potential function. So you can go back, review, you can watch my lecture notes on it from last year, or you can just remember it now. So suppose that functions m of xy and n of xy are continuous and have continuous first order partial derivatives on the open rectangle. So they give us this continuity and differentiability requirement. I'm just going to shorten all of that because the whole thing is in the book. So theorem says that let function m of xy and n of xy be continuous plus differentiable, and then you clearly see it because they're functions of two variables that we're talking about partial derivatives and then over the region, not only on the domain. So then the differential equation, so DifEq, right? M of xy dx plus n xy dy equals 0 is exact if and only if, which is the if, right? Partial of m in respect to y is the same as the partial of n in respect to x. So if that's the case, in Calc 3 we said we can find the potential function whose gradient would be our problem, actually. And we do that through integrating. So let's take a look at the example, which is technically a review of what you guys learned the last semester, if you learned it. If not, well, you're learning it now. So let's take problem, I don't know, 33 is fine, whatever. 3x squared plus 2y squared dx plus 4xy plus 6y squared dy equals 0. So 4xy plus 6y squared equals 0. All right. So first of all, those of you who never seen this before, it looks weird, right? Because dx and dy are separated. But just think about moving this dx to the other side and then dividing dx back and dividing the 4xy plus 6 into the other side. So you will actually have a differential equation that was dy over dx equals negative whatever 3x squared plus 2y squared divided by 4xy plus 6y squared. So yeah, you can actually massage this and you can get dy dx equals everything else, which means that, and you should do that. I remember as a student doing that many times, every time I see the problem like this, because it didn't make sense to see it this way. Well, I knew it from Calc 3. But you want to be able to recognize which types of differential equations can be solved this way, how they look out of the box. This is already, ready for you because m and n, right? So here is your m, here is your n, and then you start taking these partial derivatives and doing stuff. So hopefully you will flip this around at home and try to make sense out of it. So first of all, I need to check the exactness condition. If the equation is not exact, we can't do the procedure. So partial of m in terms of y is just 4y, right? And partial of n in respect to x is 4y. So it passes the condition. You must check this, because I might troll you on a test and just give you something and say, you know, here is the... Ooh, where is that? I actually have in my office somewhere, I don't know where, an awesome problem that has this thing over 3 lines of text, variables and stuff. It looks awful. It says find the potential function for it. And then on the bottom of that page, there is a little troll face and says not exact. But the problem looks awful, right? It will take hours if it was. So yeah. So you have to check for exactness, and if it is exact, then we do the procedure. So exactly. So we start with one of these and integrate. And then take the partial derivative of it and equal it to the other one. And that should do it. So start by integrating m, right? Or should I say, the notation is different, so all right. So m is equal to 3x squared plus 2y squared. And we are going to integrate that one in respect to dx. So I'm going to write 3x squared plus 2y squared dx, whose integral is x cubed plus 2xy squared. And then I'm going to say plus, I should say plus c, but I'm not going to. I'm going to say plus g of y. So why am I saying plus g of y? Because it's not only the constant that you can have there. You can also have y to the 7th power. Because if you differentiate y to the 7th power in terms of x, you're still going to get this. Does that make sense? Everyone? So in the eyes of these multivariable functions, if x is the boss, right? If x is the main variable you want to focus on, then y variable becomes a constant in that. Yeah, you hold that constant. So that's why you have to put plus g of y rather than plus c. So that's that new weird part if you haven't taken Calc 3 before. So now, technically, this is already somewhat a solution to your differential equation. But you can do better because you can determine g of y. Now, the way you do this is you take the partial derivative in respect to y, and you set it to the n from your equation. So you take the partial derivative here of x cubed plus 2xy squared plus g of y. You take the partial derivative in respect to y, and you set that equal to n. So what we get here is the partial derivative, x cubed dies. The partial derivative of this in terms of it's going to be 4xy plus g prime of y, because you are taking the derivative. Well, you are taking the partial derivative of the function that is just y, so it's just a basic derivative. And that is equal to n. Now, why we can do this? Well, I said earlier that the mixed partial derivatives are the same. That's why you have to have the exactness condition, so that you can actually set this to n, which is 4xy plus 6y squared. which is n, which came from above. So now you see that these terms die, and you have that dg dy is equal to 6y squared. Integrate both sides, boom, boom, and I mean move y first, obviously, separable equation. We get that the g is equal to over 3, so 2y cubed plus c. Now this time you have the vanilla integral, which means you have your plus c. And look what you got. You got your g of y. What is g of y equal to? You already have a partial solution to your differential equation right here. All you need to do is to add this piece that is g of y for g of y. That's all you need to do. So copy and paste x cubed plus 2x. So x cubed plus 2xy squared plus 2y cubed plus c. So that's the f of xy, right, in implicit form again. Can't solve it for y equals everything else. And that is your actually general solution to the differential equation. If you have initial condition, plug it in, get the c, and be done. Good luck. Now this is studied. You all guys took Calc 3? Because it's the entire, how many did not? Please, hand high up. So 2. You can see me either during office hours. I still have to talk about last part. But see me either during office hours or just watch my stream from Calc 3 on my channel where you find these lectures. And if you want me, I will gladly email you the Calc 3 notes, the PDFs that I have. Actually, you know what? I'm just going to email that to the whole class, and then whoever opens it, opens it. So look at your RVCC email. I'll email the notes where I did this. Now, in Calc 3, we actually do this on a 3D as well. So you actually have to do this procedure twice, over and over. So this is actually an easier problem, what we do in DifEq, than the one's done. So. Like this would be introductory problem for DifEq. Cool. The last part of this lecture is reducible second order differential equations. So that is the last part. Reducible second order. Ordinary differential equations, ODE. And the idea is that now you have a second order. Second order equations are the ones that have the independent variable, let's say t or x. We used x so far. So x, then you have y prime, and you have y double prime, right? So this is what we have as the second order equation. And what we can do is we can come up with a change of, it's not just change of variable, because you are going to say the new variable p is going to be equal to y prime from before. So you say that p is equal to y prime, and which is good old dy dx from your equation. And then if you differentiate that one, you get the second, which is p prime is equal to y double prime. Then plug in and good luck. Because it either ends with separable exact, it ends up with something, okay? So let's immediately do the example. We have 1 minute and then 2 minutes after that. Reducible second order problems 43 through 54. So you have quite a number of exercises. Any one is fine. How about 49 looks bad enough. Where we have y double prime plus y prime squared equals to y prime. Yeah. So I'm going to say that p, which is the new variable, is y prime, which means that the p prime is y double prime. And I'm going to plug all of that in. Now, y stays y, right? So if I plug all of that in, I get y, and then y prime in terms of the... okay. So we'll deal with that. Then you have yp prime plus p squared is equal to yp. So your equation now became first order, no more second derivative. So that's what I mean by reducing the order. You reduce the order by doing that. Okay, now what? Let me just check one thing. So how much is y? From this equation here, y is equal to what? Exactly. Right? Because y prime is, right, you have that p is equal to dy dx, move dx with p, because p is the function of x, integrate both sides, you get y is the integral of p. So that plugs in as well, and look what you get. You have integral of, it's supposed to be, well, let's see. So integral of p dx times p prime plus p squared is equal to the integral p dx times, I can put p in front, trying to see if I can do the integrating factor here, but it's a minus, so I can't separate. What the hell is going on? Yeah, I'm rushing to try to get into the time, which just ran out. So I'll have to actually, unless you want to wait. So yp prime plus p squared is y p prime. Oh, if I divide through by y, then I have only one y with its one integral. Hold on. So if I divide through by y, I have the p prime plus p squared over y is equal to p. Much better, right? So at this point, we can Can I? No, I can't separate. This is p. If I move p, I can't use integrating factor. What the hell is going on? Did I copy this problem right? I don't see the method that we can use actually right off the bat. Y double prime plus y prime squared is equal to y prime. Good. So plug in p is y prime, then p prime has to be y double prime because we differentiate it. And then to get y alone is you integrate both sides, so y cancels the derivative and p picks up the integral, and then that's that. When you plug everything in, your y prime double prime is replaced by p prime. The y prime is replaced by p, and then it's going to be squared, equals to y stayed y, and then p replaced y prime, and then I divided through by y, and I got this mess. This is not separable. I can't do integrating factor because of the, I have p squared and p. Writing y as the integral doesn't help. I'll have to meditate on this because we're already 2 minutes over time. I'll meditate on this and we'll start next class with this first to take care of this issue. Fair? Mm-hmm. But you have 5 days to enjoy it, and then you can also tell me, right? So I'll fix this. I just don't see the method now. And we're already 4 minutes over time. And I'm hungry. All right, bye stream.